Yeah,
Devashish. Yeah, I'm still from
right.
hiding under the curtain because my video is viewing.
So then, anyway, I also
Yeah.
is your camera on?
Yeah, it's on.
Yeah, Devakshis,
Yeah.
uh,
Professor,
I
Sitaram
can
is
see and
also
hear
there.
all of you. I did not switch on my video because the link is little bit unstable. So I
huh.
just put the video off, but I can say I hear and view all of you perfectly.
Okay, very good.
So
So,
yeah, so may I request SMS as the from the ISI Alumni Association to initiate saying something, right?
yeah, I will say that, but let
Yeah,
me
yeah.
tell you one thing. Due to certain personal problem, I will have to leave in the middle.
Okay, okay.
So after that, some of you should take over.
Yeah. I think all of us are here. And I'll be also online, so I can also take care of it.
Yes.
And I think
So,
Rudra is also
yeah,
there.
yeah. Ruddra's
So
office is
right.
very near,
Yes. So if
opposite.
any problem, the Rudra I think can help.
Yes. So,
Yeah.
okay. So thanks for arranging. But anyway, there is some time. It's still some people. Vivi is there. I saw.
Yeah,
Yeah, I saw you, Vivi. Huh?
yeah. How are you all?
Yeah.
Uh, okay. We will talk today evening.
Okay, okay.
Huh? We will talk today evening. Huh?
Yeah.
Because
Professor Sitaram is also here.
Sitaram is there. Very good.
Yeah,
So Gadadhar, am also. But anyway,
I saw. Yeah,
today is a very bad weather in Calcutta. There is a cloud burst, very bad weather. So we are doing it,
Yeah,
online only. And so
right.
did you send to others also, Bibi? You had asked me
Yeah,
whether.
I sent to B. Rajiv and Supriyo and so on. Yeah.
Acha, acha. So I have sent. Okay. How are you doing?
Okay, fine. Otherwise, good.
You heard about Tandradi?
About?
Tandradi? Tandra Rao?
No,
You didn't hear?
no, what happened?
She passed away day before yesterday or yesterday.
Who?
Tandra Rao.
Tantra now? How
Hmm.
come? Oh, I did not know that.
Hmm.
Oh,
I
ah,
thought you would know, so I didn't call you.
correct, correct. Yeah, no, I did not know at all.
Partho told me, Partho Majumdar.
Ah,
He told me.
oh,
Anyway, I am also quite a bit,
hello. Yeah, yeah.
at home. So, but
oh.
I immediately your thing came to my mind to
Yeah,
verify,
yeah,
but
right.
only to verify. But
I did not know that at all. Okay, okay.
yeah.
Mm-hmm.
Okay. So, Sitaram, you are there? Sitaram? Somebody said Sitaram is there?
Yeah, he's there. Maybe he's.
Yeah.
Hello, Sitaram. How are you?
I'm fine.
Okay, very good. Very nice to. Today, Calcutta has a very, very bad weather. There was a cloud burst, and everything has gone topsy turvy in Calcutta.
Sitaran, you have the Bluetooth.
Yes,
Bluetooth on.
yes, we do.
You should
We do.
speak.
Yes, it is also being recorded on
Talk.
YouTube, and it
Bluetooth
will be
should
available.
talk.
It is not a
Bluetooth.
live streaming on YouTube, but it is being recorded on YouTube. So there is still 5 minutes of time, and so YouTube is already on. I can see that. YouTube is
Okay,
on.
okay. I will come
YouTube.
back in 5 minutes. Yeah.
Can we mute it for the time being?
Yeah,
Because we are talking many
Yeah.
things.
So they can get.
Later on.
Hello. Hello.
The difference on them.
What happened?
Hello?
Yeah, what happened? I mean,
Yeah, I
nobody
can't
is
see the
talking.
screen anymore. Yeah,
Yeah.
and the screen is not visible for some reason.
No, everything
Sangabalu
is
No,
is
there is
visible.
no screen. He has not yet shared the
Okay,
screen.
okay. No, I mean, screen is this screen. Okay. Yeah, fine.
He has
No,
not yet shared the screen.
by
First,
screen, I mean that nav room, no, that was, I think, just went on the side for my, okay, now you can see it.
Okay.
Should I
Then
try that?
Gadadhar is there.
No, it's sharing the screen. Should I try and then if everything is all right?
If you want to check something,
Yeah.
yes, please. Oh, sorry. This is
I can.
you check that everything is all right.
Mm.
I can see you.
No, where is the? Oh, where is my?
Now you can talk.
no.
Switch off the visual.
If you switch off visual, you should also switch off the voice.
No, I'm not able to share.
Is there anybody Thangavelu to help you there?
Yeah.
Yeah, I mean, there should be Pritam or the other person from CSC.
Yeah.
Uh,
Oh, Pritam from CSC. We also have one Pritam. Yeah.
mhm.
No, but Thangavelu is in his office. There is nobody from CSC here.
Even then, I mean,
Let me check if Pritam or
any,
somebody.
yeah, in case of any problem, I think you can ask Tapon to call them, because I told
Hmm.
Tapon that they should be around and they should be.
Yeah, I'm not able to share.
Yeah, I'm calling.
Yeah,
Huh?
that's why I have to say
The
that
share
little
button
before it
is
should be
there,
done.
green button in the bottom. You can see
It
that,
is.
right?
দেখো নাহলে
No, it is there, but it's not sharing.
Okay.
আমি ওটাই একটু আগে চেক করে দিতে বলেছিলাম তপনকে।
You're now removed.
হুম।
You've removed you. I removed you.
Oh.
Show my name.
Not able to share. Yeah, that's why this. Yeah, it's okay. Maybe
So
close
share
it.
the screen.
This is the one.
So go to the Zoom.
Stop becoming
Share.
Share the
Not
desktop.
showing it.
not video part. Show
Systems.
Open.
You don't have to go there, right? I don't know why I do.
Show my video, then you have to get it up.
Green button बोल
Green button.
No.
Share.
Do I have the permission to share?
Yeah,
you have
put
permission
it,
to share.
Yeah.
But then I'm
No,
not.
no. Do it from there. Yeah. Do it from here.
Here again. That's what I did.
Hmm.
After that, it comes here.
Sure.
Then it is.
You're saying what?
But this desktop is not coming. Enter screen thing should come.
শুন আসছে না ডেস্কটপে ওটা থেকেই করছি
There should be something called Windows.
Yeah, content only side by side. This is. বললাম আসতে।
ওদের দিক থেকে কিছু করতে হবে ওখান থেকে
লগ ইন করে বসে আসবো যা কিছু এখানে
এখানে একজন
No,
কাউকে তো
usually
আসতে হবে।
ইউটিউবে শেয়ার করে
the
Let me try to do this.
I can share. I'm thinking I can share.
I think.
So I think you entered by clicking the link, right?
Yeah.
I also did the same thing. I don't know what's happening. What operating system is this?
Safari. Yeah, this.
Maybe that's the problem.
No. See, there should be one.
Yeah, no,
This
as
is
I
only
entered
the
here,
file.
so several files are, all my open windows are here. But here there is no open window.
Documents.
Yes, screens.
Advanced.
You try to click in one of them. No? Oh, it's giving exclamation.
Yeah, it's not showing.
Host पे permission दिखा दो। तुम्हार computer से बोले भालो होता है। It's a Safari or something. अच्छा होता तो। Yeah, this. I mean, I think it's a mismatch between the operating system.
No, I have given lectures in this.
Yeah, but you may have to do something.
Can you just log out and log in again?
আমরা নিচে পুরো ওই সেমিনারটাতে বসে আছি অনেকজনের আছে তো
Settings maybe. Share you. No, hello.
Allow Zoom box
Yeah.
to share your screen.
You have to give some permission.
Yeah. On.
Are you the
On.
host? Only probably host can share.
Yeah, that's the problem.
No. He can share from the other thing.
The host has to give the permission, probably.
No, it's leave meeting.
Leave.
Now share.
Oh,
Yes,
yeah.
yes, now it has gone.
Yeah. No.
Yeah, okay.
Yes, finally it's there.
Good.
Mm.
Yeah.
Some more. Okay.
No. Yes.
Sorry.
This. No, full screen.
Command
Full screen.
Okay. Let me just a few words.
Yeah.
And already time is there.
Wait. My audio is on. Yeah, video is on.
Yes. Yeah, it seems to be. Okay, so some technical problem and just sit down. Actually, today Calcutta has a very, very bad weather. There is a cloud burst and things have got topsy-turvy. So we are doing it only on online mode. And this is the 13th year we are having Somesh Bagchi Memorial Lecture. And I'm very grateful to Tangavellu, Professor Tangavellu, if I should say, our old friend, and also he knew personally, and they have collaborated, interacted at least with Somesh Bagchi. I know that. I have seen both of them together. And I thank him very much on behalf of ISIAA. And let me take a little bit of liberty and say also on behalf of ISI, Stat Math Unit Kolkata. I hope nobody will mind that. And I hope the talk will go without any hitch. And thanks for joining. And now I welcome Tangavellu and invite him to give his talk. Come, Tangavellu. By the way, Tangavellu needs no introduction. He's really very, very well known.
Yeah. Right. So, thanks, SMS. For taking it up here. And may I request Professor Tangavellu to say a few words about HTV also, and from your personal feeling before you start your technical talk.
Yeah. Thank you very much for giving me this opportunity to give S.C. Bakshi Memorial Lecture, but I'm not very happy to give a memorial lecture for S.C. Bakshi. I wish it is his birthday or some other celebration, but anyway, I still vividly remember my first visit to Kolkata. Somesh Bakshi invited me to visit ISI for 2 weeks in April 1988. And then I took a train from Chennai and I was coming, and Somesh was supposed to meet me at the station. But then I got down from the train, but the crowd was so overwhelming. I was no way wait for. I didn't know where to wait for him, so the crowd was just pushing me out. So I just came out, and then there was no phone at those time. So I simply took a taxi and then came to the campus, and Somesh was waiting for me somewhere, and then he came back later, much later. So that's the first time, I mean, I visited ISI, and that memory is still very vivid. And after that, I have met Somesh so many times and became a very good friend of mine. And I mean, I think I have already mentioned somewhere, I think in his obituary or somewhere else, that Somesh treats everyone equally, whether you are a younger person or a elderly person, you are a professor or you're a student, whoever it is, he treats everyone equally well. I mean equally well, not ill-treating anybody. So that way, Somesh was a unique person. I mean, everyone misses him, and I too miss him a lot. But whenever I come here and I remember him, but it is so sad that he's not with us. But anyway, it's nice that the Alumni Association of ISI is conducting this SEB Memorial Lectures every year. And I don't want to say that I'm happy, but yeah, I'm willing, I'm here to give this lecture, and I'm dedicating this lecture to Somesh. And it's a very, I think I will start my lecture. It's a very simple topic, and some ongoing work which I'm doing with my student Rahul. And so I think it should be accessible to more people, including the students. So I'm going to talk about an orthonormal family of operators, and the operators are defined in such a way that they mimic the definition of the Hermite functions. So I don't have any other better name for these operators, so I'm just calling them operators a la Hermite. So let me begin by the definition of the Hermite functions. So for L2 of Rn, there are so many orthonormal bases for L2 of Rn, but the most well-known orthonormal basis for L2 of Rn, in my opinion, are the Hermite functions. And the Hermite functions are defined, so they are going to be Hermite polynomials H alpha x multiplied by the Gaussian e power minus half mod x squared, and there will be some normalizing constant C alpha. So that way, phi alpha x are the normalized Hermite functions. They are defined by this equation. Anyway, the Hermite polynomials of degree mod alpha, I'm directly going to the n-dimensional case because there is no need to define the one-dimensional case and then just define them as a product of one-dimensional Hermite functions.
Are the screens moving? I don't see.
So is it moving, or anybody has any?
No,
You have to
Not
go to
yet,
the
not
page
yet.
2, I think.
Yeah. Only the title page is showing.
it's only the title page.
Oh, it's not moving now?
No.
Not yet.
See, there is a sign for that on the right-hand side panel for changing page number.
But it's
Yes, downward arrow. Try that.
But that's what I'm trying. Is it moving, or at least slowly?
No.
No.
Cancel the sharing once and
Do it again?
yeah. Sharing the পাশে থাকে আমারটাতে আছে তো stops here. Yeah, and then share it.
Share it again. This one, right?
Yeah.
That's what I clicked.
Yeah. So now it is.
Now the next page has come.
Oh, okay.
But is it?
No, but
able
you get rid of this. How to get rid of this? This
No,
panel
this I
is
can.
not. Yeah.
Yeah, that
Make
can.
it small.
Okay.
Yeah. Now here you can change.
Fine. Is the
Okay.
slides moving now?
Yes.
Yes, now
Yes.
it's moving.
Yes, now it's moving.
Yeah, you can use this also. Yeah.
Make it full screen.
Yeah, bigger one. Oh,
Yeah, go to full screen if you can.
full screen. Full screen mode. Like you sit down and then you listen to me.
Because I'm very poor.
Yeah. Let me see if the screen moves. Is it moving?
Not now.
Oh,
No, not moving.
It was moving few seconds back.
oh, maybe.
Can you click on the screen once? Sometimes it gets stuck. If it's in full screen mode.
Has the screen been shared?
Yeah.
This one, I think, right? No, which one is
No,
that?
no, no.
It's
I already opened. This is the one.
Right-hand side corner, there is a click for, if you click something, it will become full screen. Right-hand side corner.
Okay.
Is it moving now?
I cannot see anything.
No.
Now
There
we
is
can
no
see only
screen
a
now.
vertical toolbar. Yeah.
Oh, I don't know, with full screen mode.
But is it working in this mode only? Is it possible?
Can you see the screen now?
No.
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 No, sir.
Is it
Oh,
shared?
I think you have to stop share and
I'll
reshare
share it
again.
again. Yeah.
yeah.
But how many times could you do?
No, let's see once. Share. Now is it visible?
Yes.
Yeah,
Yes.
Yes, yes,
If I
yes.
move, it's moving,
Yes, now it's moving. Yes.
You can do in this.
now it's all right.
but then it's not the full screen mode. That's why I increased.
It is all
Then
right.
let's manage with this.
Yeah,
It's
no,
all
Yeah.
right.
I don't think it matters. You
Yeah,
perhaps,
yeah.
yeah.
It's all right.
That's
It's all right.
good.
Yeah,
That's good
yeah,
that
it's
you
fine. Look
continue.
fine.
Yeah. Yeah.
Yeah, this is fine.
Moving? Okay. So let me start all over again. So the helmet. It's okay. So these Hermite functions phi alpha are defined by this equation. So the h alpha x is the polynomial, and then h alpha x times e power minus half mod x squared is by definition given by this minus 1 power mod alpha, alpha the derivative of e power minus mod x squared. That's how it is defined. Now it is, yeah. Do you see the next line now?
Yeah.
Yes, sir.
Yeah.
Okay. So here we choose a constant C alpha so that the functions phi alpha are normalized in L2 of Rn. That's what, so I mean, I want the L2 norm of phi alpha to be equal to 1. That means I have to choose my C alpha by this equation. C alpha per minus 2 is the integral of h alpha x squared with respect to this measure, e power minus mod x squared dx. Anyway, the C alphas are well known. I mean, explicitly known, one can compute because these are polynomials, and then we have the Gaussian, and it's given by this equation. C alpha per minus 2 is pi power n by 2, 2 power mod alpha times alpha factorial. So with this definition, one can, well, with the definition given above, that is not difficult to show that they form an orthonormal system. That is, we have the inner product of phi alpha with phi beta is given by the Kronecker delta and delta alpha beta. That means they are orthogonal to each other when alpha not equal to beta. When alpha equal to beta, the norm L2 norm is 1. And they form an orthonormal basis for L2 of Rn. By this I mean I can take any L2 function and then expand it as f equal to summation inner product of f with phi alpha times phi alpha. So these are the Hermite coefficients of the function f, that is the inner product in L2 of Rn. And this series is supposed to converge in the norm, L2 norm, and that can be verified. So for every function f, we have an Hermite expansion which converges in the norm to the original function f. And there is a vast literature on the study of convergence of the above expansion for f coming from LP when p not equal to 2. For p equal to 2 is almost trivial because it's Hilbert space theory. They form an orthonormal system, and then using actually Weierstrass theorem for continuous functions, expanding a continuous function in terms of polynomials that can be used to prove the completeness of the system. But when we go to p not equal to 2 and then take f in LP of Rn, still we can form this formal series because phi alphas are nice Schwarz class functions, so we can take the inner product with any temper distribution even. So the LP functions, we have a formal expansion, but it's not true that they will converge. So there is a vast literature. And Hermite functions appear naturally in several contexts and they possess several magical properties. Some of the properties we will recall them later. Now let us now shift our attention to another Hilbert. Is there any question? Now we can shift our attention to another Hilbert space that is consisting of boundary linear operators acting on L2 of Rn. So let me define Hilbert-Schmidt operators. Start with a boundary linear operator T acting on L2 of Rn. Let's say that it is Hilbert-Schmidt if this norm of T Hilbert-Schmidt squared is given by this series. So T star is the adjoint of T and T star T is a non-negative operator. Apply T star T to phi alpha, take the inner product with the phi alpha. And if I take T star T to the other side, then it actually this becomes norm of T phi alpha squared. If this series converges, then we say that T is a this is one way of defining Hilbert-Schmidt operators. Well, we can replace this phi alpha, this orthonormal basis by any other orthonormal basis, and then we can define Hilbert-Schmidt operators. And let me denote this set of all such operators by S2, and this becomes a Hilbert space. In order to make it a Hilbert space, we need an inner product, and the inner product between two such operators is given by this series. Again, this is summation alpha, all the multi-indices, S star T applied to phi alpha, inner product with phi alpha. Then the series converges because T and S are Hilbert-Schmidt. So S star T will be a trace class operator. So this converges. So this S2 becomes a Hilbert space. And L2 of Rn and S2 both are separable Hilbert spaces. Therefore, any two separable Hilbert spaces are unitarily equivalent. So there is a unitary operator taking L2 of Rm onto this S2. So we can start with any orthonormal basis for L2 of Rm, and that will give rise to an orthonormal basis for S2 and vice versa. But we are particularly interested in a family of unitary operators, which I call them pi lambda, where lambda is a non-zero real number. So this pi lambda is going to take L2 of R2n onto S2. So S2 consists of Hilbert-Schmidt operators acting on L2 of Rn, but then this pi lambda is taking L2 of R2n onto S2 as a unitary operator. And then we will choose a suitable orthonormal basis for L2 of R2n. So L2 of R2n, we can choose any orthonormal basis. In particular, we can choose a Hermite orthonormal basis, Hermite functions on R2n. But here we will choose an orthonormal basis psi mu lambda, depending on lambda. Now mu has to come from the multi-index n power 2n. And this will give rise to a family of operators on the other side. So pi lambda takes L2 of R2n onto S2. So I have an orthonormal basis for L2 of R2n and apply this pi lambda, you get an operator. That operator we can call it S mu lambda, and this will be an orthonormal basis for S2 because this pi lambda is a unitary operator. I will define this pi lambda. So these operators share several properties of the Hermite functions, and the analogy is so striking, so we are tempted to call them operators a la Hermite. So again, I said since I don't have any other name to call, so I'm just calling operators in the style of Hermite. So here this basis I have to define suitably. I have to choose this function psi mu of lambda suitably, not any orthonormal basis. So in order to do that, so I will introduce certain non-commutative derivations, dj. So j equal to 1 to 2n. 2n non-commutative derivations I will define. And using them, I'm going to define S mu lambda e power minus half h lambda equal to some constant minus 1 power mod mu. The derivation, d power mu. So this will be defined in terms of dj's, like d1 power mu1, d2 power mu2, etc. The multi-index notation applied to this e power minus h lambda. So here I have to recall, or I have to tell what are these operators, e power minus h lambda and e power minus e power minus half h lambda and e power minus h lambda. So these guys are going to play the role of the Gaussian. If you remember the definition for the Hermite functions, then we are taking alpha the derivative of e power minus mod x squared. And then if I multiply that by that e power half mod x squared, then I get the Hermite functions after suitably normalizing it. So here the role of the Gaussian is going to be played by e power minus h lambda, the Gaussian e power minus mod x squared, and this is e power minus half mod x squared. That role is played by e power minus h half of h lambda. And here H lambda is nothing but the Hermite operator, which is, it generates a semigroup. So I'm going to work with this e power minus t H lambda, that is the Hermite semigroup. And the Hermite semigroup at t equal to 1 is on the right hand side, and then Hermite semigroup at t equal to half appears in the left hand side. And so this is playing the role of the Gaussian. So Gaussian is nothing is related to the heat kernel for the standard Laplacian, but this semigroup is related, though this e power minus h lambda and e power minus half h lambda are related to the Hermite semigroup, these two operators on Rn. So the Laplacian, let me recall, Laplacian on Rn generates the heat semigroup with the explicit kernel Qtx. If I call it Qtx, it is given by 4 pi t power minus n by 2 e power minus 1 over 4t mod x squared. Then the Hermite functions, we gave a definition of the Hermite functions by taking derivatives of the heat kernel at t equal to 1/4, and then alpha the derivative, and then multiply by e power minus half mod x squared. That's how we define before normalizing it. We can also write the definition in a different way as a convolution equation. So we can also define this phi alpha to be those unique functions which satisfy this convolution equation. Phi alpha convolved with this q half, the heat kernel at half, t equal to half, that should be equal to the same normalizing constant x power alpha times q1x. This is heat kernel at t equal to 1. So why are they same? To see that they are the same, just simply take the Fourier transform. Fourier transform, you know that Fourier transform converts convolution equations into product. So if I take the Fourier transform on both sides, I will get the Fourier transform this guy into Fourier transform this. That should be equal to Fourier transform of x power alpha times q1. And these phi alphas are eigenfunctions of the Fourier transform. That is a well-known fact, with eigenvalues minus I power mod alpha. And then the Fourier transform qt, that heat kernel, is simply given by e power minus t mod psi squared. So therefore, the left-hand side will get minus I power mod alpha, phi alpha, and e power minus half mod x squared. On the right-hand side, if you calculate, I'm taking the Fourier transform q1, but then after multiplying it by x power alpha, taking the Fourier transform of this will be nothing but taking alpha derivatives of the Fourier transform q1, and Fourier transform q1 is e power minus mod psi squared. So therefore, we get the original definition of the phi alpha. So phi alpha here, and then minus I power mod alpha, that will get cancelled with whatever something extra coming from here apart from the alpha to derivative. And you'll see that this equation is equivalent to the original definition of the phi alpha. So one can also define this phi alpha satisfying, phi alpha being the unique function satisfying this equation. So from this equation, we can holomorphically extend. So we know that the right-hand side is nothing but x power alpha e power minus, e power minus 1 over 4 mod x squared. So this is a holomorphic, this function can be holomorphically extended. Left-hand side, if you see, this is a Gaussian function. This is a nice function. So here, this side also we can holomorphically extend. And after doing holomorphically extending it, and then bringing it the e power 1/4 of z squared this side, we will see this equation. That e power 1/4 of z squared, phi alpha convolved with the q half, evaluated the complex variable z coming from Cn, that is given by C alpha z power alpha. And this I call, this the normalized monomial, I call it zeta alpha z. So the above equation connects Hermite functions with the Fock space. Because if we just go back, so we have this, whatever we have this. So this one I can call as the transform of phi alpha. I mean, I will give a name to that transform. Some transform applied to phi alpha is giving me these monomials. So the Hermite functions are connected to the Fock space. So the Fock space f of Cn is the space of all entire functions which are square integrable with respect to this weight function, some constant e power minus half mod z squared. So this is the Gaussian weight on Cn. Consider all those entire functions which are square integral with respect to this measure. And then what we know is that these monomials are certainly here in this Fock space, that can be verified. And with with the same normalizing constant C alpha that was used for the Hermite functions, they also become an orthonormal basis for the Fock space. So on the right hand side. So they form an orthonormal basis for f of Cn because f of Cn consists of all the entire functions. So they can be Taylor expanded, and the Taylor expansion is nothing but the expansion in terms of zeta alpha. So that can be easily seen using mean value property and such things. So this suggests that we can define an operator, a transformation, acting on L2 of Rn. So I will call it BF, and B stands for the Borgman because who studied this transformation. So Borgman transform of F evaluated at Z is taking the convolution of F with the heat kernel at t equal to half, holomorphically extend, and then multiply by the e power 1/4 Z square. Then we can show that this BF belongs to f of Cn. That means it's an entire function, square integral with respect to the Gaussian weight function e power minus half mod Z square. This can be verified. And the definition of the Hermite functions, the second definition of the Hermite function we gave, that simply means that the Borgman transform takes the normalized Hermite function into zeta alpha. And zeta alpha is also normalized, and they also form an orthonormal basis for f of Cn. That is again easy to verify, integrating everything in polar coordinates. So that means this, not because of that, B actually one can show that B is a unitary operator taking L2 of Rn onto f of Cn, and it takes the Hermite functions onto the monomial zeta alpha. And another way of defining this Borgman transform is, you just expand it. The heat kernel is a convolution. So there is a translation of the heat kernel involved, translation of the Gaussian involved, expand the Gaussian, and then you will see this definition. So Borgman transform of f is defined to be just take f, multiply by this Gaussian, and then take the Fourier transform, but in the imaginary direction. There is no I here. So Fourier transform in the imaginary direction, multiply by e power minus 1/4 of Z squared. That is another definition, not another definition, same definition written, expanded version. Now, instead of Fock spaces, we can also consider a family of Fock spaces, family indexed by lambda real, which I call them twisted Fock spaces. And they are going to be precisely the space of all entire functions that are square integral with respect to a weight function depending on a parameter lambda. So now I'm considering f lambda on C2n, entire functions of 2n variables. They are going to be square integral with respect to this weight function. So some normalizing constant, e power minus half lambda, hyperbolic cotangent lambda, mod z squared plus mod w squared. Then we have this exponential of lambda times imaginary part of z w bar. So this is a weight function, and you just observe that as lambda goes to 0, this converges to the previous e power minus half. So this becomes 1, e power minus half mod z squared plus mod w squared, and this disappears. So it reduces to the ordinary or classical Fock space when lambda equal to 0. And these Fock spaces are related to the twisted Siegel-Borgman transform or the twisted heat kernel transform, we can call it, because the earlier one, the Borgman transform is related to the heat kernel transform because f going to f convolved with the heat kernel at t equal to half. They are related. And here they are related to another twisted Siegel-Borgman transform, and it is related to another heat kernel, but not the Euclidean heat kernel, but related to the heat kernel on the Heisenberg group and its derivative. So as expected, there is a twisted Borgman transform in the background, which is given by twisted convolution with a heat kernel that is associated to the twisted Laplacian. And the twisted Laplacian is going to be associated to a sublaplacian on the Heisenberg group. And the heat kernel I'm talking about, that is going to be related to the heat kernel on the Heisenberg group. But I will just define them explicitly so that I don't have to recall the definition of sublaplacian, Heisenberg group, etc. We can avoid that. So the heat kernel that appears in the definition of the twisted Borgman transform is not the Euclidean one, but it's one associated with the twisted Laplacian. And this is the heat kernel I'm talking about. So without defining twisted Laplacian, I'm just giving you the kernel. So the kernel is a function on R2n. It is given by pt lambda x comma u is this constant lambda by sin h t lambda power n. This is the Gaussian e power minus lambda by 4 hyperbolic cotangent t lambda times mod x squared plus mod y, mod x squared plus mod u squared. So this is the heat kernel. Hello? Morning. Yeah.
Where? Can I ask them to mute?
I think, okay.
No, let me ask them to mute it.
Yeah.
Should we? Let me request.
I think they have stopped. Yeah. They have realized it.
I request everyone to please mute yourself and only unmute when you have to ask a question.
So let me continue. With this heat kernel, when I'm going to, anyway, the twisted Bargman transform is going to be given in terms of twisted convolution. So I have to define the twisted convolution. So twisted convolution can be defined for any parameter lambda not equal to 0. And lambda equal to 0, it's becoming a convolution. So the lambda twisted convolution between two functions f and g on R2n is given by this expression. So we have the same. If this exponential factor is not there, it is just the convolution. All we have is, what we have extra is the c power minus I lambda by 2 u dot x prime minus x dot u prime. And this is again coming from the convolution structure on the Heisenberg group by taking the Fourier transform in the central variable. So, there are people who are familiar with these things, but for others who are not familiar, you can just simply take this to be the definition. There is a twist in the convolution. So with this twisted convolution defined by this equation and this heat kernel Pt lambda, this is the heat kernel associated to the twisted Laplacian. The transform is defined by this one. So take a function f in L2 of R2n, twisted convolve with p half lambda t equal to half, and then divide by this heat kernel at t equal to 1, and then some normalizing constant. And this extends holomorphically. So we get an entire function, and this we call the twisted Bargman transform. And this one, we are defining it on L2 of R2n, end up with getting entire functions. And we can show that those entire functions are precisely belonging to f lambda of C2n. These are the twisted Fock spaces. And more importantly, this twisted Bargman transform becomes a unitary operator from L2 of R2n onto f lambda of C2n. Because these twisted Fock spaces were defined in terms of twisted Bargman transforms some time ago. But then later, an interesting relation between the Fock space and the twisted Fock space was discovered by Venkunaidu and Shubham Bais. Actually, they first looked at the Siegel-Bargman transform, twisted Siegel-Bargman transform for the twisted Laplacian, that's also called the special limit operator. So they gave a different proof of the image of this twisted Siegel-Bargman transform by making a clever change of variables. And the same change of variables allows me to find a relation between the Fock space f of C2n and the twisted Fock space f lambda of C2n. And this plays a role in defining our Hermite operators. And the the relation is simply given by a very nice linear transformation. Let me define C lambda taking. Sorry about that. So this is a linear transformation. It's defined from C2n to C21. It's given by, so it's a dilation factor. Sigma lambda acting on Z comma W is, let me use this notation. C lambda stands for hyperbolic cotangent, S lambda stands for hyperbolic sine. I think this is wrong. This is hyperbolic cosine, not cotangent. So C lambda by 2 Z minus I times S lambda by 2 W, comma, C lambda by 2 W plus I times S lambda by 2 Z. So this is a transformation. So they did some explicit calculations and then came up with this transformation. So if I take this transformation and then define this operator T lambda, this will take a function f on C2n into another function T lambda f on C2n. In order to define T lambda f at Z comma W, simply evaluate f at sigma lambda applied to Z comma W. So this becomes a surjective isometry between the Fock space into f lambda of C2n. So this is easily verifiable. So simple calculation, simple, but it's lengthy calculations, but this it's not difficult to verify this one. So this gives me a relation between the ordinary Fock space and the twisted Fock space. Here lambda is not equal to 0. Lambda equal to 0, this becomes the identity operator. See, the above relation between the twisted and classical Fock spaces has some interesting consequences. Let's see. So for example, if I apply this T lambda to zeta mu are the monomials. So now we are in C2n. So mu is coming from n power 2n. So this is z comma w power mu. So that can be defined. It's a monomial. So apply T lambda, that means zeta mu at sigma lambda z comma w. It's this b lambda. So this becomes an element of, zeta mu becomes an element of f lambda C2n. I'm sorry, zeta mu evaluated at sigma lambda z comma w becomes an element of this one. But this b lambda is a twisted Bergman transform, that is a unitary operator. So every element here is of the form b lambda of some function f coming from L2 of R2n. So there exists unique functions psi mu of lambda coming from L2 of R2n, such that if I apply b lambda to psi mu lambda, then I should get this operator, this function T lambda of zeta mu. So written out explicitly, what we have is, this is the definition of the twisted Bergman transform applied to this function psi mu lambda. So Cn lambda P1 lambda z comma w inverse this function convolved with, or lambda twisted convolved with P half lambda, that should be equal to, so this is a monomial, and this is also homogeneous function of degree mod mu. So something comes out because of the dilation factor. And what we have here is C lambda to Z minus I S lambda by 2W, C lambda by 2W plus I S lambda by WZ, this to the power mu. So that's what we get. So these functions psi mu of lambda are defined by this equation, or satisfy this equation. So this uniquely determines the functions. And this is the analog of the equation which was satisfied by the Hermite functions. For the Hermite functions, we wrote another equation, right? So phi alpha convolved with this q half equal to some constant x power alpha q1, right? So we got another definition of the phi alpha as a convolution equation, and this is the similar analog of that equation for these functions psi mu lambda. And then it is easy to see that, it's clear that these guys form an orthonormal basis L2 of R2n, because psi mu forms an orthonormal basis for the standard Fock space, and d lambda takes that orthonormal basis into an orthonormal basis for f lambda, the twisted Fock spaces. And therefore, since this is nothing but the b lambda star applied to that zeta mu lambda, that should be an orthonormal basis for L2 of R2n. We will give another description of these functions later. Right now, let's work with those, the definition given by the convolution. So in order to define the operators, the operators a la Hermite, we make use of the Weil transform that sets up one-to-one correspondence between L2 of R2n and the space of Hilbert-Schmidt operator. Initially, I mentioned that we will choose a unitary operator. So I'm not choosing an arbitrary unitary operator between L2 of R2n and S2, but this particular unitary operator, which I call the Weil transform. So the Weil transform is going to be defined in terms of a family of unitary operators indexed by x comma u. So pi lambda x comma u, these are unitary operators acting on L2 of Rn. And these Weil transforms are going to be defined in terms of this pi lambdas. I'm using the same notation. But these pi lambda xu are unitary operators explicitly defined by this one. Here phi is coming from L2 of Rn, it's a function. And I translate the function by u, and then there is a modulation involved, e power I lambda x dot psi plus half x dot y plays the role of modulation. And this translation followed by this modulation, that is my operator, pi lambda. And this is a unitary operator, that is easy to see. The map x comma u going to pi lambda x comma u defines a projective representation of R2n. And this can be lifted to a genuine representation of the Heisenberg group. So those representations are called the Schrodinger representations of the Heisenberg group with the parameter lambda. And then I'm restricting them to the to Cn part of the Heisenberg group, getting these unitary operators. So that's why they form a projective representation for Cn or R2n. And using these unitary operators or unitary operator valued function, I can define the Weil transform. So start with an L2 function, I mean L1 intersection L2 function in order to define without any trouble. I can integrate f against this operator valued function. So this is an integrable function, these are unitary operators. Then I will get an operator. So this this integral converges in the operator now. And this, then we can show that this f going to pi lambda f initially defined for f coming from L1 intersection L2, that one can show that this is actually a Hilbert-Schmidt operator acting on L2 of Rn. Therefore, using the density of L1 intersection L2, this can be extended to the whole of L2 of R2n, and that becomes a unitary operators between L2 of R2n and this space of Hilbert-Schmidt operators. So that is the unitary operator I was talking about. This pi lambda is a unitary operator taking L2 of R2n onto S2. And then using this unitary operator pi lambda, I can define an operator S mu lambda, simply applying pi lambda to psi mu of lambda. So this psi mu of lambda, remember that this is the function corresponding to zeta mu lambda, which is an element of the Fock space F lambda, which we got by applying the operator T lambda to the monomials zeta mu, which is an orthonormal basis for ordinary Fock space. So from ordinary Fock space, we have elements of the twisted Fock space by applying the operator T lambda. That is an orthonormal basis for the twisted Fock spaces. And then these psi mu lambdas are associated to those orthonormal bases by inverting or applying the adjoint of the twisted Boltzmann transform. So this psi mu lambda form an orthonormal basis L2 of R2n, and pi lambda is a unitary operator between L2 of R2n and S2, and S mu lambda are defined to be pi lambda of psi mu lambda, so they form an orthonormal basis for S2, and these are the operators we are interested in. So I think I have explained it here. So zeta mu lambda is given by applying T lambda to zeta mu, and then psi mu lambda are defined by this equation. And then I have applied pi lambda to psi mu lambda in order to get these operators. Now we can take can apply the Weil transform to this defining equation. And then we are going to use another property of the Weil transform. So we have this twisted convolution between two functions f and g. So now I can take the Weil transform of this convolution, and it turns out that the Weil transform converts this twisted convolution into products. Like the ordinary Fourier transform converts standard convolution into products, this pi lambda converts twisted convolution into products. So this pi lambda of this guy will be pi lambda f composed with pi lambda g. So if I apply this pi lambda to this one, I have this pi lambda of psi mu lambda, that is our definition, S mu lambda, and pi lambda of p half lambda is coming here. On the right hand side, I have pi lambda applied to the product of this monomial times pi p1 lambda. Fortunately, we know explicitly what is this pi lambda of p half lambda, and we can also calculate the pi lambda of zeta mu lambda times p1 lambda. And this can be calculated in terms of the Hermite semigroup. So now we need to recall the definition of the Hermite semigroup. We have defined the Hermite functions, and we also mentioned that the Hermite functions are eigenfunctions for the Fourier transform, but they are also eigenfunctions of the Hermite operator H. By the Hermite operator, I mean this operator, minus Laplacian plus mod x squared. And the eigenvalue corresponding to this, Hermite function is 2 mod alpha plus n. So the spectrum of this is well known. So 2 mod alpha plus n. Mod alpha is an multi-index. And from this standard Hermite function, I can also scale them and define these curled Hermite functions. Phi alpha lambda equal to mod lambda power n by 4, phi alpha of square root of mod lambda times x. So these are also eigenfunctions of the scaled Hermite operator H lambda. So this is minus Laplacian plus lambda squared mod x squared. So H lambda applied to phi alpha lambda becomes 2 mod alpha plus n mod lambda times phi alpha lambda. So this is easy to verify. And this operator H lambda, now here we assume that lambda not equal to 0. If lambda equal to 0, then I get the ordinary Laplacian. So this H lambda generates a semigroup, which is called the Hermite semigroup, T positive, and this is a boundary linear operator acting on LP Rn, e power minus T H lambda, whose kernel can be calculated explicitly. So the interesting fact about this semigroup and the kernel Pt lambda associated with twisted Laplacian or the special Hermite operator is the following one. This is going to play a role for us, because if I take the Weyl transform, remember that Pt lambda is a function on R2n in L2 of R2n. Actually, it's a Schwartz class function. I can apply pi lambda to this. I will get a Hilbert-Schmidt operator. That operator is nothing but e power minus t h lambda. That means, in some sense, Pt lambda can be called the generator of this Hermite semigroup. So this actually becomes a pseudo differential operator, and hence it's an integral operator with the explicit kernel, and that kernel is the kernel of this Hermite operator. So we can write it explicitly. So in the previous equation, when we apply pi lambda, then we have to calculate the Weyl transform of two things: pi lambda of p half lambda, and another one is the pi lambda of this guy, zeta mu lambda times p1 lambda. In order to do this, we have to introduce, in order to calculate this operator pi lambda applied to this one, we are going to introduce certain non-commutative derivations. So now we can start with say densely defined linear operator A, need not be bounded, acting on L2 of Rn, and then take any bounded linear operator and then define this operator dA acting on T to be the commutator of T with A, that is TA minus AT. Of course, this has to be well defined, and it's a densely defined operator. This will be defined as a densely defined operator. So this I call the derivation of this. So this operator A gives rise to this derivation dA. So we call this as a derivation or a non-commutative derivation for the following reason, because if we apply this dA to product of two operators, then what we get is, it's very easy to verify. The derivation applied to t times s plus t times derivation applied to s. So this is like the derivative applied to the product of two functions, any partial derivative applied to product of two functions. So this also satisfies a similar property. So these are called non-commutative derivations. The most important non-commutative derivations we are going to use are these derivations dpj and dqj, where pj and qj are the momentum and position operators coming from quantum mechanics. So pj is simply the partial derivative of the function, and qj is nothing but multiplication of the function by psi j, the jth coordinate vector. See, these two operators are going to play an important role. We'll see. That's because in order to calculate pi lambda of zeta mu lambda p1 lambda, so you have to recall that zeta mu lambda is zeta mu evaluated at sigma lambda applied to z comma w, and sigma lambda applied to that gives terms like this: c lambda by 2 z minus s I lambda by 2 w comma something, and to the power, the whole power mu. So we need to calculate. So now we have restricted those functions to R2n, and then there are functions of x and u, and then we have to calculate. So that will be a product of terms of this to the power mu j, etc. So we have to calculate the Weyl transform of this kind of functions. Essentially we have to calculate pi lambda of xj times p1 lambda, pi lambda of uj times p1 lambda. So in order to do that, we have this nice formula. So as I said, we have to calculate the Weyl transform of xj times f and Weyl transform of uj times f, and there are these formulas. Pi lambda of lambda times xjf is nothing but I times this derivation related to the momentum operator applied to pi lambda of f. So take the Weyl transform of f and then apply this derivation. Then you get pi lambda of lambda times this. And if you want to calculate the well transform of UJF, all you have to do is take the well transform and apply this derivation corresponding to the position operator. So therefore, we are led to consider this kind of derivations. dj for j lying between 1 and 2n. For j lying between 1 and n, this dj is going to be I times c lambda by 2, this derivation with the momentum operator, and minus lambda s lambda by 2 derivation with respect to the position operator. And dj plus 1 is coming from the other component. So lambda c lambda by 2 dqj minus s lambda by 2 dpj. So these are the non-commutative derivations which I mentioned in the beginning. And then when mu is a multi-index, we simply define d mu equal to d1 power mu1, d2 power mu2, etc. So we can show that these derivations are forming a commuting family of derivations. So they commute, so there is no ambiguity in defining these products. So these are all operators, derivations. So they are commutators of operators. So there is no problem in defining them uniquely. So in terms of these derivations, if we go back, I had this pi lambda of p half lambda that gives me the Hermite semigroup at t equal to half. And this is pi lambda of psi mu lambda. That is our definition of S mu lambda. So S mu lambda times e power minus half h lambda is equal to, there are some constant. And this derivation applied to P1, the well transform of P1 lambda, that is e power minus h lambda. So this derivation applied to e power minus h lambda, and then there are some constants coming, constants are explicit. And so this is the defining relation. So we can define our operators. Our operators satisfy this equation. This we can also start with this definition and then proceed. And we can see the similarity between this definition of S mu lambda and the definition of the Hermite functions. Here we have the derivative of the Gaussian. Here we have the derivatives, non-commutative derivatives of the Hermite semigroup at equal to 1. And that is equal to our Hermite function times the Gaussian e power minus half mod x squared. And this is our Hermite operator, or operator of Hermite type, times the e power minus half h lambda. This is the Hermite semigroup at equal to half. So this is the analogy. So we can take this to be the definition of S mu lambda and then work backwards and then show that they form an orthonormal basis for the space of Hilbert-Schmidt operators. So this is the result I'm just stating. For the Hilbert space of Hilbert-Schmidt operators equipped with this inner product, then these functions, family of operators defined by this equation, form an orthonormal basis. So now we can investigate some more properties of these operators, S mu lambda, bringing out further analogies. So in the classical situation, let's recall these annihilation and creation operators of quantum mechanics. D by d psi j plus lambda psi j, we call it aj. I'm just suppressing the factor lambda. You can assume that lambda is positive from now on. Aj star is the adjoint minus d by d psi j plus lambda times psi j. And if I apply them to the Hermite functions, they have this kind of action. Aj star applied to phi mu, the phi mu is getting converted into phi mu is getting converted into, I think I forgot lambda here, phi mu plus ej, and then square root of 2 mu j plus 2 times lambda comes out, and aj applied to phi mu lambda is phi mu minus ej square root of 2 mu g lambda. So here this aj decreases the degree and then aj star increases the degree. So in quantum mechanics, they call it the annihilation operator, and then this is the creation operator. If we apply this operator to the initial one, the Gaussian mu equal to 0 case, so it gets killed. But if you apply aj star to the Gaussian, then you get the next Hermite function, and apply it again, get another Hermite function of higher order, etc. So we can create all the Hermite functions starting from the Gaussian and applying this operator. That's why they play an important role. So similarly, so there are, well, those relations can be proved by simply multiplying, applying these operators to the original definition. we can do the same thing here. So S mu lambda e power minus half h lambda is given by this equation, applying d mu to this e power minus h lambda. So if I apply one more dj to this side, then you will see that this is a derivation applying dj, then dj applied to s mu lambda times this one plus s mu lambda times dj applied to this one. On the other side, this if you apply dj here, then this mu getting converted into mu plus ej. So d power mu plus ej applied to this one is modulo some constants. It is just s mu plus ej lambda times e power minus half h lambda. Then we have to adjust the constant because c mu lambda getting converted into c mu plus ej lambda. So then we get this factor. So in the classical case, this was 2 mu j plus 2 square root of that into square root of lambda, but now we have square root of lambda times sin h lambda. This follows from this one. We don't have to do any work, just apply this. But then we have to calculate this dj applied to e power minus half h lambda. In the classical situation, this is the partial derivative of the Gaussian, then we know that it is just multiplication by psi j. But here also it is not difficult. The operator, we can call it mj. mj equal to dj applied to e power minus half h lambda and then multiply by this e power half h lambda. So this we can call it an operator mj. And then whatever we have defined earlier, I mean doing this calculation, if I define a new operator script aj acting on t to be dj applied to t times mj, this is a multiplication operator, then what we have is aj applied to s mu lambda is this one square root of this times s mu plus ej lambda. So we can see the analogy between aj, this script aj applied to s mu lambda and an aj star applied to few mu lambda. So that creates, I mean, there is a change of notation here because for some reason I'm just calling it aj instead of calling aj star, because aj star will be defined as the adjoint of this one. So we see the analogy between this one. And this mj also can be calculated very explicitly. So this aj plays the role of the creation operator in the operator setting, and its formal adjoint, I'm calling it script aj star, that will play the role of the annihilation operator. And the operator mj that occurs in the above definition also calculated explicitly. In order to do that, all we have to do is recall this operator, the momentum operator and position operator, and aj and aj star can be written in as linear combinations of these two guys. So therefore these derivations can be put in this form. Earlier we defined them in terms of dpj and dqj. Now we can also write them as a linear combination of daj and daj star. So for j lying between 1 and n, dj is given by this, and j lying between n plus 1 and 2n is given by this one. So linear combination of this kind of derivation. But then aj and aj star, the action of these things on the Hermite semigroups is not easy, not difficult to calculate, because aj, the action of aj and aj star on the Hermite functions is very explicit. If I do some simple calculations, then we can easily verify that this daj applied to the e power minus half h lambda simply brings out this aj times the aj. So it is like taking partial derivative of the Gaussian, you get the psi j times the Gaussians. Here we can also think of this h lambda as sum of aj star plus aj star aj. So it's like taking derivative with respect to the operator value, think one. So it brings the operator aj. So we have to be careful. This has to be placed on the left. Similarly, aj star, if I apply daj star to the Hermite semigroup, then it brings down aj star to the left. So in terms of these things, we can calculate this dj applied to this. This is my operator mj. That will be simply this multiplication operator qj times e power minus half. And dj plus 1 will be this multiplication by this pj. So that means I have explicit expression for this script aj and script aj star. And so this operator aj is going to look like this, and aj plus 1 is going to look like this. So if I apply aj to s mu lambda, we get this one, it creates, and aj star. So aj star I'm defining as the formal adjoint. So I didn't calculate explicitly, but it can be done. So AJ star applied to this, it decreases the eigenvalue. So it becomes S mu. So this is another analogy between Hermite functions and its operators of Hermite type. And there is one more analogy. The Hermite operator or the scaled Hermite operator. So this can be factored or can be written as in terms of AJ and AJ star. This is a well-known factorization. Half summation AJ, AJ star plus AJ star AJ. And then similarly, so this suggests that I consider on the operator setting, I consider this operator. I have AJ, AJ star plus AJ star AJ, take the sum and then take half of that. So this is the this is the analogous operator. I don't know what to call this. Analogy. In analogy with the Hermite operator, we have an operator. This operator is acting on operators. And so we have this scaled Hermite operator applying to phi alpha lambda gives me this eigenvalue 2 mod alpha plus n times mod lambda times phi alpha lambda. So this script h, if I apply to s mu lambda, then we can verify that it gives me 2 mod mu plus 2n times lambda sin h lambda becomes the eigenvalue corresponding to the eigen, I don't know, eigen, cannot call them eigen functions, maybe eigen operator of this thing, whatever it is. H applied to s mu lambda is this into s mu lambda. This is another analogy. I think one can calculate, I mean, the H is defined and AJ, I know, AJ star I can calculate. So I can write down some expression for the script H also. And then we have to see whether that is some well-known operator or not. I haven't done that. So now we can, some examples of this S mu lambda to get some feeling. When mod mu equal to lambda, mod mu equal to 1, then we can calculate, we only have to calculate dj applied to this and then see what we get. And if I apply dj to e power minus h lambda, again, this is the commutator with something. And then commutator of some AJ, commutator of this semigroup with AJ and AJ star are explicitly, we can calculate them explicitly, and then it turns out to be this operator. And dj plus 1 applied to this turns out to be this operator. So this is a linear combination of, so from this we see that S ej lambda or S mu lambda when mod mu equal to 1, they are linear combinations of this AJ e power minus half h lambda and AJ star times e power minus half h lambda. Or more generally, we can show that there exists a non-commutative polynomial p mu lambda, and s mu lambda is nothing but this polynomial evaluated at this vector aj, and this is the vector aj star times polynomials in 2n variables of degree, say, mod mu, then times e power minus h, h of lambda. So the operators s mu lambda are going to look like this. And these are all nice operators. So these are all, we can just show them. So this is a nice pseudo differential operator, and these are all differential operators. And this is going to be a pseudo differential operator satisfying very nice decay conditions. They are going to be operators of type 0 and uniformly bounded derivatives, etc. And so you can use some known results from pseudo differential operator theory to show that they're all bounded on LPRN. Initially, we defined them as Hilbert-Schmidt operators acting on L2 of Rn, but they're also bounded operators on LP of Rn for any P lying between 1 and infinity. And there is another easy way of checking that these are all bounded operators on LP of Rn, that is transference theorem due to Maucheri. So according to this theorem, if I can show that the map taking f going to f twisted convolution with psi mu lambda is a bounded operator on LP, then the Weil transform that psi mu lambda, that's going to be a bounded operator on LP of Rn. That is a transference result. This operator has to be bounded on LP of R to n. Then the Weil transform this function, the convolution kernel here, that will become a bounded operator on LP of Rn. That is the transference theorem of Maucheri. But then these guys are defined implicitly via convolution equation. Right now, we don't have much information except that they are in L2 of Rn, R to n. But then we will show that they are actually very explicit and they are Schwarz class functions. And therefore, this operator, convolution with a nice function. So it is bounded on any LP, including 1 and infinity. And the Maucheri's theorem implies that these guys, these are the well transformed, these nice functions. So they are bounded on LP of Rn. That's another proof. And why do I say that these functions are very nice functions? That's because there is a very simple relation between Hermite functions and these functions. Hermite functions on R2n and these functions. So initially I had no idea whether these functions are how these functions are going to look like, but then it turned out to be very simple relation between Hermite functions and these functions. Again, just go back to the relation. So we have this relation. We have zeta mu, and then we apply t lambda to this one, and then that is we call the zeta mu lambda, and then so this is an element of the twisted Fock space. So and then applying b lambda star to these things, I get this function psi mu lambda. In other words, the twisted Bargman transform of psi mu lambda is equal to this one, and this is nothing but t lambda composed with the Bargman transform, because zeta mu is coming from phi mu. These are the Hermite functions without any scaling. Apply the Bargman transform, we get zeta mu, and then apply this transformation which takes Fock space into twisted Fock space. Then we get this one. T lambda composed with B applied to phi mu is B lambda applied to this one. In other words, psi mu lambda is nothing but B lambda star composed with T lambda composed with B applied to the Hermite functions. But then this operator turns out to be a very simple operator. This operator is going to be very simple dilation operator. Call it d lambda. So d lambda, so it's acting on the functions of 2n variables. D lambda f of, at x comma u is simply given by f square root of lambda by 2 hyperbolic cotangent lambda by 2 applied to, this is the dilation applied to x comma u, and this is normalizing so that L2 norm is 1. So this is the operator, very simple operator. And psi mu lambda is simply dilate, so I don't know, I want to call them deformation, deforming the Hermite function by this factor. So these are nothing but the deformed Hermite functions. And this, again, this is very easy to, I mean, the proof is not at all difficult, direct verification. And because of that, these guys are also eigenfunctions of another Hermite operator, deformed Hermite operator. So I will call it minus Laplacian plus, in place of lambda, I'm using lambda by 2 hyperbolic cotangent lambda by 2 squared mod psi squared. This is an operator on acting on functions of 2n variables, and apply this. These are eigenfunctions with this eigenvalue. So these are nothing but Hermite functions, sort of. So therefore, because the Hermite functions give can also be defined in terms of a nice generating functions, and this relation allows me to give a nice generating function for our operators S mu lambda. So again, I'm recalling a generating function for the Hermite function phi mu. So phi mu x comma u zeta mu z comma w, that is given by this one, e power 1/4 z squared plus w squared, e power minus half. So this is the Gaussian translated by z comma w. This is something dividing by the heat kernel at t equal to 1. So in the same way, the operators S mu lambda are also given by Taylor coefficients of an entire function. Here these phi mu are given by the Taylor coefficients of this entire function. Here I will have an operator valued entire function, and the Taylor coefficients will be given by S2. So in order to get this generating function, all we have to do is apply the pi lambda, the Weil transform, to the above generating function. Before doing that, initially I defined this pi lambda for x comma u, x and u real coming from Rn, but we can also extend them holomorphically. I think there is something missing. Can also extend them holomorphically. Pi lambda of z comma w can be defined as densely defined unbounded operators. And then consider this operator. So this e power minus half h lambda is a nice operator. So this is an unbounded operator. This is another unbounded operator. So you have pi lambda of iw minus iz. Here this is pi lambda of minus of this argument. So I'm just conjugating. So we get an operator valued function. So this turns out to be a nice Hilbert space valued, no, operator valued entire function. G lambda z comma w. So this is taking values in S2 that can be verified. And so this I can call the translated Gaussian. I mean, this is the analog of the translated Gaussian. So this is the translation of the, can say the translation of this operator e power minus half h lambda. There is a reason to say that this is a translation. And then what we have is, so on the generating function identity for the Hermite function, we have on the right hand side, we have some function and then some entire function. And then we had this translated Gaussian, but now replace the translated Gaussian by this translation of the operator e power minus half h lambda. This is g lambda. And the left hand side is, there are some dilation factors because of that. And the s mu lambda is given by this generating function. By this, I mean, just look at this the entire function taking values in S2. And if you want to calculate S mu lambda, simply calculate the Taylor coefficients and then just you get this one. So this is a generating function identity. And I think this generating function identity will be useful in studying further properties of these Hermite type operators S mu lambda. I think that's all I have to say.
Let's thank the speaker.
Yeah,
thank you, Ravi, for the nice talk. And are there questions or comments? Are there any questions or comments?
Yeah, I have just one question.
Yeah.
You see, we have the two variable Hermite polynomials also, right?
Yeah.
HXT. Your lambda corresponds to T or what? I didn't understand.
No, lambda is a dilation. Just changing the operator minus the plus plus mod x. Yeah.
At some stage, you talked about that e to the power of minus T h lambda.
Yeah, this is a semi-group. T is positive.
Correct.
Yeah.
So from there, are there any two variable Hermite polynomials coming out or no?
No, I'm just talking about n variable Hermite polynomials.
Yeah, no, but we have got this T and you see, we have got u to the power of xt minus t square by 2, right?
Yeah.
And a sort of polynomials in x and t, so that they are solutions of the
no. You mean
equation,
the
right?
heat polynomial? You mean heat polynomials?
Oh, I see. Okay.
Yeah, they are called heat polynomials. I'm not talking about heat polynomials here.
Oh, they are heat polynomials. I didn't know that.
Yeah,
Okay.
they are also related to the Hermite polynomials evaluated in the imaginary directions. Yeah.
Oh, I see.
Yeah, maybe one can also, what will be the analog of those guys? Operator analogs of those guys may be an interesting problem.
I see. And throughout your lambda is positive, right?
No, you don't have to assume that lambda is positive, because if I don't assume lambda is positive, then AJ lambda, that action becomes, for lambda is positive and lambda is negative, the different action. So in order to avoid that, I assume lambda positive.
Okay. Thank you. Thank you. Very nice.
More questions or comments? If not, then let me just have a very this kind of comment. I mean, just kind of think that this talk reminds very earlier work of my ABC and Partha Sai Chakravarti. I think I saw Partha in the.
Yeah, there could be some relation. I don't know. Operator people, quantum.
So we did a small work on some case study of non-commutative geometry called the quantum plane. So is while algebra and this thing. So some operators, I think, just came up there also. I mean, just
pi lambda. Pi lambda.
Right. So that. See, it was of course a completely different perspective and a completely different work, but some analogs of these operators. I think the one you call the star and plus edges, edge star plus edge star, we called it as non-commutative Laplacian on that while algebra, and we calculated some kind of analogs of geometric quantity like volume form and so on. So it is just it's very nice to see that from a different perspective from your talk. Thank you very much. So I suppose that there is no other comment and so on, and let me thank again for for all these technicalities and rain and everything. But in spite of, you could at least deliver the talk online and we could send to it. So let's thank the speaker again. And okay, so I so I'm sure the office staff will assist you to go back to your guest house, and your car is booked for tomorrow, of course. Tomorrow, I think weather will be not bad, so it should not be a hassle. You can leave the Zoom maybe. So let's thank.
How do I leave?
Attending.
Yeah, see. Okay.
There is a door sign on the right.
Yeah.
Yeah.
There is a door on my left also. Yeah, I will use the right door first.